Hello and welcome to Controllers Tech. Few months ago I covered a video explaining how to interface a servo motor with STM32. The motor I used in that video was a 180 degrees servo motor, which rotates between 0 to 180 degrees based on the pulse of the input PWM signal. Today I have with me another kind of servo motor, a continuous rotation servo. As the name itself suggests, this servo rotates continuously throughout 360 degrees, and we can control its RPM by varying the width of the input PWM signal. Here I have both kinds of servo motors with me. You can purchase these from the Controllers Tech store. Both the motors look identical, with literally no difference from a visual point of view. You have to rely on seller's information about which one is 180 degrees, and which one is continuous. Some of these motors do come with the label on them, but not all have it. Here I have a servo tester, which will be used to test these servo motors. The tester has 3 different modes available to test the servo motor. This select button can be used to switch between the modes. I will use the manual mode, as it is used to vary the width of the PWM signal. This servo tester can be used to test up to 3 servo motors simultaneously. This is the output end of the tester, and we will connect the motor here. The motor has 3 wires, red is the VCC, brown is the ground, and yellow is the signal. Let's connect the wires to the tester output pins. I am connecting the second servo also, and we will see how both these servos behave with the PWM signal. Towards the input of the tester, I have connected the VCC pin to the 5-volt battery, and ground to ground of the battery. Let's rotate the knob to vary the width of the PWM signal. You can clearly see the behavior of both servos, when they are provided with same signal. The 180 degrees servo changes its position based on the width of the PWM signal, whereas the continuous rotation servo changes the RPM. Also note the direction of rotation of the continuous rotation servo. When the knob is at extreme end, the continuous servo is rotating at high RPM in clockwise direction. When the knob is rotated, the RPM starts decreasing, and the motor stops when the knob is at the center. At this moment, the 180 degrees servo is also rotated through 90 degrees. And now when the knob continues to rotate, the RPM of the continuous servo is increasing again. Also the 180 degrees servo rotates through another 90 degrees, completing the full 180 degrees rotation. As I mentioned, there are other modes available on the tester. The neutral mode sends a pulse with the width of 1 milliseconds, whereas the auto mode changes the width very fast, and we see an output like this. Let's see the pulse output on the analyzer. Here I have a logic analyzer, and I will connect the signal pin from the tester output to the channel 1 of this analyzer. Let's rotate the knob to one extreme end, and check the pulse on the analyzer. The frequency of the signal is 50 Hz, which is standard for any servo motor. Note that the pulse width is 880 microseconds. Now I am rotating the knob towards the middle, till the point where the servo stops rotating. The pulse width is 1.5 milliseconds at this point. Now I am rotating it to the other end. Here we have the width of 2.1 milliseconds. So we saw the RPM and direction of the motor varied by varying the width of the PWM signal between 0.9 milliseconds to 2.1 milliseconds. Actually, this goes even more extreme than this, and I will show it when we write the code. So let's start the CubeIDE, and create a new project. I am using STM32 CubeIDE. Give some name to the project, and click Finish. Let's start with the clock setup first. I am selecting the external crystal to provide the clock. The Bluepill board has 8 MHz crystal on it, and we will run the system at 60 MHz. I am choosing 60 because most of the STM32 MCUs can run at this clock frequency, so if you have some confusion, you can set the clock as per this video. Note that both APB1 and 2 timer clocks are running at 60 MHz. The timer will use this clock to generate the output signal. Each timer is either connected to APB1 or APB2 bus. You can check the datasheet of your MCU to confirm which bus it is connected to. I have already made a video explaining the PWM generation in STM32, you can check it out in case of any doubt. Since both the APB timer clocks are at the same frequency, I don't need to worry about the timer's source. Now go to Sys, Debug, and enable serial wire. Let's configure the timer now. I am using the timer 1 to generate the PWM signal. Set the clock source to internal clock. Now enable the PWM generation for channel 1. You can see the pin PA8 got configured as the PWM output. We will connect this pin to the signal pin of the servo. Let's configure the parameters now. We need to generate a signal with a frequency of 50 Hz. Here is the formula to calculate the frequency of the PWM signal. We have the timer clock at the same frequency as the APB2, which is 60 MHz. If I set the prescaler to 1200, and the auto reload value of 1000, the output frequency will be 50 Hz. The ARR value plays an important role, as the width of the signal is calculated with respect to this value. I will explain in a while why I chose to input the ARR value of 1000. Let's set the prescaler value to 1200. Also set the ARR value to 1000. Whenever you are setting these values, the value should be 1 lower than the desired value. This is because the code at the register level adds a 1 to this value. Click Save to generate the project. We know that the servo motor uses the signal width from 1 millisecond to 2 milliseconds. This is a standard for any servo. But when I was testing it, I found that the motor was responding from 0.5 milliseconds to 2.5 milliseconds, so I will consider these values. The pulse has a frequency of 50 Hz, which implies that the period is of 20 milliseconds. A width of 0.5 milliseconds out of 20 milliseconds is equivalent to 2.5% duty cycle, and a width of 2.5 milliseconds is equivalent to 12.5% duty cycle. Now let's assume that we set the auto reload value to 100. In order to vary the signal between two extreme ends, we only have a difference of 10 steps between them. So each step would have a major change in the pulse width. On the other hand, if we use the auto reload value of 1000, the duty values will change to 25 and 125. This will result in a total of 100 steps between the extreme values, and so our output signal will have more variations. Alright, let's write our code now. Inside the main function, start the timer in the PWM mode. I am using the timer 1 channel 1 for the PWM generation. The compare register is where we set our pulse value for the duty cycle. Here I am setting the value to 25, basically one of the extreme ends. Let's build and flash the project to the board. You can see the servo motor is rotating with very high RPM. If we check the output on the logic analyzer, we can see the pulse has a width of 0.5 milliseconds. The frequency of the output signal is almost 50 Hz. Now I am setting the pulse value to 50, which will result in the signal with a width of 1 milliseconds. You can hear the sound of the motor to note the difference between their speeds. The speed has been reduced compared to the previous value. Now we will set it to 75, which will result in a pulse of width 1.5 milliseconds. And this will stop the motor, just like it was stopping when the knob was in the middle. Setting the value to 100 will result in a pulse of width 2 milliseconds. The motor is now rotating in the counterclockwise direction. You can see the pulse width is 2 milliseconds. And in the end we will set it to 125, which will result in a pulse of width 2.5 milliseconds. Note the sound of the motor. The speed has been increased to maximum. So we can see the motor is responding for the pulse of width between 0.5 milliseconds to 2.5 milliseconds. We will write our code with respect to these values. Let's define a pulse variable to store the pulse value, which we will set to the compare register. I am setting the initial value of 75, this is where the motor stops. Now I want to gradually increase the RPM of the motor in one direction, and then in the other direction. So our pulse value is at 75 right now, and we will increase it until we reach 125. With each step, the value will be passed to the compare register. Let's give a delay of 250 milliseconds between each step. When the pulse reaches 125, the motor will be at the maximum RPM in the counterclockwise direction, and this while loop will exit. Then we will start reducing the pulse value, and we will keep doing it until the value reaches to 25. When the pulse is reducing, the motor will start slowing down, and it will stop when the pulse is around 75. Then with the further reduction in the pulse value, the motor will start rotating in the clockwise direction, and its speed will keep increasing. When the pulse value is near 25, the motor will rotate at maximum RPM in the clockwise direction. At this point, this while loop will exit, and the first one will run. The pulse will start increasing again, and the motor will start slowing down. The motor will stop when the pulse value is near 75. The pulse continues to increase, and the motor will start rotating in the counterclockwise direction. The entire loop will continue forever. Let's build and flash the project to the board. Hear the sound of the motor to get the idea about the speed, and please ignore the background noise. You saw the motor was responding how we programmed it to do. We were able to control the RPM of the continuous servo motor using the PWM signal. In the next video, we will see how to use the potentiometer and a button to control the RPM and direction of this servo motor. This is it for the video. You can download the code from the link in the description. Leave comments in case of any doubt. Keep watching, and have a nice day ahead.